Have you ever really stopped to think about what's happening when you send a message? I mean, your data zips from your screen to a server halfway across the globe in what, less than a second? It feels like actual magic, right? But it's not. It's this incredibly complex, coordinated dance of technology. So today, we're going to follow a single click and see just how deep this rabbit hole goes. All right, so you just hit send. That one little click, it kicks off this journey of absolutely epic proportions. Your message, doesn't matter if it's an email, a photo, a meme, it's about to travel thousands of miles through this insane web of cables, routers, and switches. But how? How does it know where to go? And how in the world does it get there so fast? That's exactly what we're going to unpack. So the secret behind all this magic isn't really a trick at all. It's just a set of really, really well-designed rules. Think of it like a universal language that every single connected device on the planet has agreed to speak, and that language, it's called a protocol. A protocol is quite literally the foundation of everything. Just like we need grammar to make sense of sentences, computers need protocols to make sense of data. And these rules cover the whole shebang, the exact format of the data, what to do if there's an error, even the timing of the digital conversation. Without them, honestly, the internet would just be a bunch of digital static. Okay, so before your data can even think about hitting the road, it's got to be packaged and addressed correctly. And this isn't just a one-and-done thing. No, it's a series of steps, kind of like a digital assembly line, where each stop adds a new layer of instructions for the journey ahead. Yeah, this whole process follows what's called a layered model. It kicks off right at the top with your application, writing your email. Then, as that data moves down the line, it gets prepared for travel. It's broken up into smaller, manageable pieces. Each of those little pieces gets its own digital address label. And then finally, it all gets converted into the actual physical signals. We're talking light pulses or electrical charges that are going to physically travel through the wires. The technical term for this whole process is called encapsulation. And at each step, a new header, which is basically just a chunk of control info, gets added. The slide mentions nesting dolls, and that's the perfect way to think about it. You're putting your data in a box, then that box in another box, and so on. Each box has different instructions for a different leg of the trip. So, okay, the package is ready. Now what? How does it actually get where it's going? So our data is all packed up and ready to go. But now we've got to make a really, really important distinction. You see, there's the thing being sent, and then there's the system that decides how to send it. It's the difference between the mail itself and the mailman. And in the world of networking, that's the difference between a routed protocol and a routing protocol. Let's really drill down on this because it's key. A routed protocol, like the famous Internet Protocol, or IP, that is the mail. It's the actual data packet. But the routing protocol, stuff like RIP or BGP, that's the mailman. That's the intelligence, the system that reads the address on the packet and uses its map to figure out the absolute best path for that data to take. So to be super clear, routing protocols don't actually carry your data. Not at all. What they do is carry information about the network itself. This lets the routers, which are basically the traffic cops of the internet, make really smart decisions. These routers are constantly chattering with each other, building and updating their own internal maps of the internet, what we call routing tables. Okay, now here's a cool detail. The journey your little data packet takes isn't guided by one single giant map of the whole internet. No way. Instead, it's handled in two totally separate phases. First, it has to navigate its local neighborhood, and only then does it get to travel on the huge global highways that connect all those neighborhoods together. So when your packet first leaves your computer, its very first job is to find the exit out of your local network, whether that's your office network, your university campus, or your internet service provider's network. And all of that local navigation, that's handled by something called an Interior Gateway Protocol, or IGP for short. A really classic example of an IGP is a protocol called RIP, the Routing Information Protocol. Now, RIP is what we call a distance vector protocol, which sounds complicated, but the idea is super simple. It decides the best path based on one single thing, the hop count. A hop is just passing through one router, so all RIP cares about is finding the path with the fewest possible stops along the way. Simple as that. But how does a router using RIP even build its map in the first place? Well, it starts out knowing basically nothing. When you first turn it on, its entire world consists only of the other routers it's physically plugged into. That's it. Its view of the wider network is incredibly small. But then,
the talking begins. About every 30 seconds, these routers just shout out their entire routing table to their immediate neighbors. It's exactly like neighbors leaning over the fence and yelling, "Hey, I know a shortcut to the grocery store. It's only 2 blocks this way." All of a sudden, a router starts learning about parts of the network it had no idea even existed a minute ago.
And this is the discovery phase. The router takes that new info from its neighbor and compares it to what it already knows. It might see, whoa, my neighbor knows a path to the server that's only 3 hops, but my current best path is 5 hops, so it updates its own table with the better route. Now imagine this happening over and over again all across the network until every single router agrees on the best paths to everywhere. That final synchronized state is called convergence. It's when everybody has the same correct map. All right, so our little packet has made it. It used an IGP to successfully navigate its local neighborhood, and now it's standing at the edge, the border crossing. It's about to step out onto the global stage, to travel between massive, completely independent networks all over the world. And for that, it needs a totally different, much more powerful kind of routing protocol, an exterior gateway protocol, or EGP. And let's be honest, when we talk about EGPs today, we're pretty much just talking about one single protocol, the one that literally holds the entire global internet together. And that's BGP, the Border Gateway Protocol. It is the protocol for routing between networks on the internet, full stop. Now, remember how RIP just counted stops? BGP is way more sophisticated. It's a path vector protocol. It doesn't just care about how many stops, it cares about the specific path of networks it has to cross. You see, BGP thinks about the internet in terms of these huge networks called autonomous systems, or ASs. An AS is just a big network run by one organization. Think Comcast, or Google, or a huge university. BGP routers sitting at the borders of these ASs exchange information, and the most crucial piece of info is the AS_path. This is a literal list of all the AS numbers your packet will have to travel through. And this list is the secret sauce that prevents catastrophic global routing loops. Why? Because if a router ever sees its own AS number in the path it's being offered, it knows something is wrong and just throws that route away. So, there you have it. We've seen all the individual pieces of the puzzle, right? We've seen how the data gets packaged up, how it finds its way around its local neighborhood, and how it travels across the globe. So, let's do a quick recap of our packet's entire grand tour from start to finish. First up, encapsulation. Your email gets chopped up and packaged into nice, neat little IP packets. Next, an IGP, like RIP, guides that packet to the edge of your local network, your autonomous system. Then, at the border, the big gun, BGP, takes over. It looks at the map of the world and finds the best path of other ASs to get to the destination network. Once it arrives in the right neighborhood, it's handed back off to a local IGP to find the exact computer it's looking for. And finally, the whole process happens in reverse. The packet gets unwrapped, layer by layer, until your original email is perfectly reassembled on the other person's screen. And all of this happens in the blink of an eye. It's incredible. You know, this really brings us to the biggest takeaway of all. The internet isn't some single giant thing. It's an inter-network, a massive collection of tens of thousands of completely independent networks that have all just agreed to cooperate. They've agreed to speak the same languages, like BGP, so they can pass data back and forth. When you think about it, it's honestly one of the greatest cooperative efforts in the history of humankind. But here's a final thought. This system we've been talking about, it was designed decades ago for a world that looks nothing like the one we live in today. And as we connect billions more devices and demand ever more speed, tighter security, and rock-solid reliability, it really leaves us with a pretty fascinating question to think about. What new protocols, what new rules for the digital road will the internet of the future need?